So let's have a look at Leaving Cert question from Light and Sound. I'm looking at Leaving Cert 2009 question 7, which is mainly about diffraction. So let's have a look at this question in your notes. This is a 56-mark question. 20 minutes is the maximum time you should allocate to it. In question 7, it says, when light shines on a compact disc or CD, it acts as a diffraction grating, causing diffraction and dispersion. And they want you to explain the underlying terms. So that's just a question of writing down the definition for each. And the definitions are nice and easy. I always say, when I think of definitions, remember a key word. So what's my key word for diffraction? My key word for diffraction is spreading. And what's my key word for dispersion? It's breaking up or splitting. For some reason, a lot of students seem to mix up these two definitions. Diffraction, as you know, is the spreading of waves around corners or through gaps. 6 marks for that. And dispersion is the breaking up of light into its colours. 6 marks for that. Next part of the question. They're asking me to derive the diffraction grating formula. Look, I've done this as a separate proof. So you'll see it there along the sidebar. So have a look at that proof. There's 12 marks for it. It's the only proof actually for Light and Sound. But you better learn it. If you're doing Light and Sound, you better learn that proof because 12 marks out of 56. So it is over 1/5 of the marks for a particular question. The proof is very straightforward. You get your nice diagram, do a little bit of maths, and you've got your 12 marks in the bag. Right, let's move on now to the problem part, the intelligent part of the question now. So I suppose those 2 parts there were the mundane, stuff that you would have learned very well. Now we're on to the intelligent part of the question where we're actually going to do a problem. So you've got an interference pattern is formed on a screen when green light from a laser passes normally through a diffraction grating. The grating has 80 lines per millimeter and it's placed at a distance of 90 centimeters to the screen. The distance between the third order images is 23.8 centimeters. And in part 1, I've got to calculate the wavelength of the green light. Okay, they gave me no diagram there, so I'm going to produce my own diagram. Once I produce my diagram, it'll become very, very straightforward. So here's my diagram. I'm shining green light onto a diffraction grating. The question is to find the wavelength lambda of the green light. I'm told that the grating in question has 80 lines per millimeter. Anyway, the light passes through there, and by constructive interference, you get these bright green images formed at these different orders. N equal to 0, that's the central order. N equal to 1 is the first order, all the way up to N equal to 3. And what they tell me in this question is that the distance between the third order images, up there and down there, is 23.8 centimeters. That's all the information that I have. Well, your first step is, can you find D, the distance between any 2 lines from the number of lines per whatever? We call that the grating element. Can I find D from the grating element? And I can. You have your technique, don't you? D is equal to, if there's 80 lines per millimeter, the distance between any 2 lines is 1/80th of a millimeter. We've done that many times before. Turn the milli into its power of 10. So its power of 10 is 10 to the power of minus 3. So it's 1/80th multiplied by 1 by 10 to the power of minus 3 meters. Now I'm ready to put that into my calculator. So into my calculator, I'm going to press fraction 1/80th multiplied by 1 by 10 to the power of x minus 3 equals, and I get an answer of 1.25 by 10 to the power of minus 5 meters. That's a very standard technique that you've learned very well in your lessons. So now I want to find the wavelength. Well, the first thing you're going to do is for your 3 marks, so there's 12 marks altogether to work out the wavelength. You get 3 marks just for writing down the formula. N lambda is equal to d sine theta. I'm looking for lambda in that formula. Lambda is equal to question mark. We're dealing with the third order images. So I'm going to put n is equal to 3. D, I've just worked out. D is 1.25 by 10 to the power of minus 5 meters. Is there anything else that I need? Well, theta. I should be able to find theta from my diagram. I was told that the diffraction grating is 90 centimeters away from the screen. The one thing I always tell you when you do these problems is, they've given me the distance between n equal to 3 above and below. I just deal with the top half or the bottom half and then double up my answers because everything in the bottom is symmetric with everything on the top. So if I shade in that triangle, let me just deal with that right angle triangle. And I have enough information on that right angle triangle to work out theta. Now, if that's 23.8 centimeters from n equal to 3 up there to n equal to 3 down there, what is it from n equal to 3 down to n equal to 0? Well, as I said, everything is symmetric. So the distance of that right angle triangle, the side of that from n equal to 3 down to n equal to 0, is 23.8 divided by 2, which works out to be 11.9 centimeters. So in here, this side of the triangle is 11.9 centimeters. So from that information, I'll be able to find theta. Now, do I have to change the distance in each case into meters? Well, you don't, because you're going to divide one by the other. So you can leave it as in centimeters if you wish. So I've got tan theta. I'm going to use tan because I've got the opposite side, 11.9, and I've got the adjacent side, 90. The tan is the obvious one to use here. We're just doing some simple first or second year trigonometry. The tan theta is equal to the opposite, which is 11.9 centimeters, divided by the adjacent, which is 90. Theta, therefore, is the inverse tan of 11.9 divided by 90. So let's put that into our calculator and work it out. So shift tan, fraction, 11.9 divided by 90. Close your bracket. So be doing this calculation as I do it. And I get, say, 7.53 degrees. So that angle is 7.53 degrees. So theta, 7.53. So now I have another bit of my formula. I have theta is 7.53 degrees. Right, so I now have everything in my formula bar lambda. So now I want to work out lambda. So write your formula in terms of lambda. So lambda is equal to d sine theta. Slide the n down, divided by n. So lambda is equal to d, 1.25 by 10 to the power minus 5, by the sine theta, 7.53 degrees, all over n, which is 3. So put all that into my calculator, fraction, 1.25 by 10 to the power of x minus 5, multiplied by sine of 7.53, close bracket, all over 3. And you get an answer of, let's go 2 decimal places, 5.46 by 10 to the power of minus 7 meters. Okay, so 12 marks for that. It's a standard problem. We devised the diagram ourselves. Often they give you the diagram, but if they don't, it's dead easy to create the diagram and put all the information on it. We just applied our formula and we did our technique to find D. Moving on to part 2. Looking at my notes again, they're asking me to work out the maximum number of images that are formed on the screen. So again, this is another technique that you've done very well in your lessons. So let's look at this part of the question. We're talking about 9 marks for this part of the question. What do I have so far? Well, I have D. The diffraction gradient is 1.25 by 10 to the power minus 5 meters. We've just worked out the wavelength to be 5.46 by 10 to the power minus 7 meters. Now, what's my technique for doing this question? Well, your formula is n lambda is equal to d sine theta. How do I get the maximum number of images? Well, I ask myself, what is the maximum value of sine theta? The highest value that sine theta can be is 1. So basically what I do is I put sine theta equal to 1, and therefore, to get the maximum number of images, the formula I'm going to use is n lambda is equal to d. And what I'm looking for is the number n. The number n then will be the highest order of image that I can obtain. So writing that in terms of n, I get n is equal to d divided by lambda. That's basically all I'm going to do. There's a few other things, though, you have to think about and be careful about here. So d is 1.25 by 10 to the power minus 5. And lambda is 5.46 by 10 to the power minus 7 meters. I'm going to put that into my calculator. When I put that into my calculator, I get say 22.9. Now, n has to be a whole number. You either have an order, you either have an image or you don't have an image. So n has to be a whole number. You're going to round that off, but you're going to actually round it down. So in other words, we never quite made an order of image n equals 23. So the one before that is n is equal to 22. So whatever number you get, always round it down to the number below that. So therefore, n is equal to 22. We're still not finished. We're saying the highest image on one side is n is equal to 22. But there's also n equal to 22 on the other side. And don't forget about the n equal to 0 in the middle. So I told you the technique for working out the number of images from that. The number of images is 22 above, 22 below, and don't forget about the n equal to 0. So what do? I multiply 22 by 2 to get 44, and I add on 1 to get 45 images. So whatever value you get for n, multiply by 2, and add on 1, and that will give you the total number of images. So 45 images in total will be formed. Well, let's have a look at the last 2 parts of the question. It says the laser is replaced with a source of white light, and a series of spectra are formed. Spectra or rainbows are formed on the screen. So you've got to explain in part 3 how the diffraction gradient produces the spectrum, and part 4 why we do not get a spectrum or rainbow at the 0 order image. So let's have a look at that. Well, green light is replaced by white light. Here's my formula, n lambda is equal to d sine theta. You know, white light is made up of the colors of the rainbow, and each color has a different wavelength. But according to that formula there, if we have different wavelengths, the colors are going to be formed at different angles on the screen. In other words, they're going to be broken apart. They're going to be split. That's what gives me the spectrum. That's what we said dispersion was. It's the breaking up of white light into its colors. So here's a nice explanation. There's 9 marks for asking how a spectrum is formed. White light is made up of different colors. with different wavelengths. And according to n lambda is equal to d sine theta, each color will be formed at a different angle, which produces your spectrum. That's the point you want to make, that white light has different colors with different wavelengths, and that according to that formula, those colors will be formed at different angles on the screen. In other words, they're split. They're now in different positions. You only see white light when all the colors land on the same spot. So we get that spectrum as a result of that. So 9 marks for answering that. And then the very last part of this question, they're saying no spectrum is formed at n equal to 0. Explain. Well, at n equal to 0, look at the formula. At n equal to 0, it doesn't matter what the wavelength is. You're going to get 0 on the left-hand side, and theta will be 0 for all the colors. All the colors will land in exactly the same position. When all the colors land in the same position, they mix together to give white. So, at n equal to 0, theta is equal to 0 degrees for all colors. The colors land on the same spot, giving white. In other words, no spectrum is formed.